let's give a big welcome to that expert engineer of the elements, the adept authority of the atoms, the intrepid investigator of the isotopes, and the wonder of physics, Professor Clint Sprott.
Welcome to the Wonders of Physics. Now, this is the International Year of the Periodic Table of the Elements, upon which all of physics and chemistry is based. But Mr. Wykes, what's this I hear about changing the periodic table?
Yes, Professor Sprott, our funding agency says there's just too many elements on the periodic table, too costly to keep them all on there, and we're going to have to cut it down. So I'm going to make a version 2.0, and I'm sure we can do much better with the table.
That's ridiculous. You can't change the periodic table. The elements are what nature has given us, and they're all important. And I'm going to convince you of that, beginning with the first element of hydrogen, with our first visitor, Dr. H.
Woo, hydrogen! Yeah, let's go! Yeah! Woo! Yeah! Yeah, that's right. Hydrogen is number one of the elements. Without hydrogen, none of us would be here. In fact, none of any of this would be here. That's because hydrogen is the building block for all of the other elements. Fusion in stars can take hydrogen atoms and turn it into all the other elements. And, as if that's not enough, hydrogen is also really important for the most exciting part of physics, blowing stuff up. So, that's how we're going to start today. Now, I have here a rocket. And I have here some hydrogen. So hydrogen has a lot of energy and it makes it a really good rocket fuel. So we're going to fill up our rocket with some hydrogen gas. We'll give it another second or two so we get a really good explosion, right? Okay, that seems about good. And now I'm going to light our rocket. And I'll give you a heads up when you're going to want to cover your ears.
This is very unexciting.
Let's cover our ears, okay?
All right. Okay. Well, I guess I can be wrong once in my life.
Okay. Well, it's not all rocket science when it comes to hydrogen. Hydrogen is also 2/3 of a really important and really powerful molecule here on Earth. Let's see if you guys can guess it. I'll give you some hints. So first of all, if you consume too much of this molecule, it can cause excessive sweating. Accidental inhalation of this molecule can kill you, and this molecule is so powerful that if it falls from the sky, it can even knock down bridges and pick up cars. Anybody have any ideas? You can yell it out. Yell it out. Yeah, exactly. Yes, if you guess dihydrogen monoxide, you're right. But for those of us who are familiar with this molecule, we can just use its nickname, water. Yes, now water is all around us, and without it, we couldn't survive. But as we know, most of the water around us is usually in a liquid form, right? So it might be hard to believe that water is in fact made up of 2 atoms of hydrogen and 1 atom of oxygen, both of which normally exist as gases on their own. So I have a contraption here that will prove, in fact, water is made up of 2 atoms of hydrogen and 1 atom of oxygen. Now this process is called electrolysis. So when I flip this switch, we're going to start sending electricity through our colored water here, and it will separate into hydrogen on one side and oxygen on the other. Now it's going to take a couple minutes. So while that's doing its thing, I'm going to let somebody else make their case. I'll come back. For now, I'm going to go into my resting state over here.
Okay, Professor Sprott, I'm looking at the table on the right-hand column, and it says that those are inert gases. And inert sounds like they pretty much don't do anything. Surely we can get rid of those.
Don't call me Shirley. But Mr. Wykes, the inert elements, sometimes called the noble elements, are important precisely because they don't interact with the other elements. And our next visitor, my good friend, Duke Nobellington, will explain.
Ah, Professor Sprott, my good man. Now then, what's all this nonsense I hear about removing my fellow nobility from the periodic table? Outrageous, I say. The noble gases are the most regal of elements and have many important properties and uses.
Duke, what's wrong with your voice?
Oh, well, to demonstrate some of the interesting properties of the noble gases, I just took a big breath from this balloon here, which is full of helium, the second lightest element, and the first of the noble gases. Now, kids, I want to say, please don't try this at home. The balloons you get at the store can have helium with all kinds of harmful contaminants in it. This is ultra-pure research-grade helium, so I know there's nothing else in here. And because it's helium, I know it's inert, so it won't interact with anything in my body and won't poison me when I breathe it in. But why did it make my voice sound so funny? Well, helium is much less dense than air. That's why the balloon wants to float up when I hold it. And as a result, the speed of sound in helium is quite a bit faster than it is in air. It's about 2 times as fast. And so that shifts the resonance frequency of my vocal tract and causes my voice to sound higher. So now I've got a question for all of you. I have a second balloon here that's filled with another gas, sulfur hexafluoride. As you can see, this balloon wants to fall down. The gas inside of here is much denser than air. So my question to you is, if I breathe from this balloon, what do you think will happen? How many of you think it'll make my voice higher? Not many. How many of you think it'll make it lower? And how many of you think it'll have no effect at all? Okay, well, the great thing about physics is we can do the experiment and find out. So let's do the experiment.
That's odd. No effect at all. Must have been the wrong balloon. But if it had been sulfur hexafluoride, it would have made my voice sound much deeper. In fact, just to be safe, I'm going to take a bow and expel whatever's in my lungs.
Of course, because helium is less dense than air, we use it to make things float, like balloons and also blimps.
Yeah, but you could use hydrogen too. It's also lighter than air.
That's very true, Dr. H. And you know, people have tried that before, and it hasn't always gone that well. That's because hydrogen is quite a bit more reactive than helium, as you've already shown us. In fact, you know what? Why don't we give it a try right now?
Let's do it.
Okay, so I've got 2 party balloons here. This one on my left is filled with helium. That one on my right is filled with hydrogen. Let's see what happens when we try to light them on fire.
Why not? Okay, helium first. Let's give him a countdown. Ready? 3, 2, 1.
All right, we got a pop, but not much of a bang. That was just the rubber giving way under the heat of the match. Let's try it with your balloon.
Yeah, I'll show you what a real explosion looks like.
Yeah, I hope you're not too fond of your eyebrows.
Okay, so you guys might actually want to cover your ears for this one. Okay. And let's count down. Ready? 3, 2, 1. Okay, so now you tell me, which of those would you rather have at your next birthday party? Actually, no, don't answer it. Don't answer that question. Okay, don't answer that. Helium also has a lot of other important uses. We use it to cool things down to very low temperatures. We can use liquid helium to cool things down to just a few degrees above absolute zero, or minus 450 degrees Fahrenheit, which makes even Madison in the polar vortex sound pretty warm. And that's really important for things like medical imaging and also physics research.
Okay, so maybe we can keep helium, but what about the other noble gases? I've heard really bad things about radon.
Yeah, all right, okay. You sort of got me there. Radon is sort of the black sheep of the noble gas family, and it does live down in the basement. But even radioactive elements like radon are important. Here, I'll show you. Over here I have what's called a cloud chamber. You can see it up on the 2 screens on either side of me. Now, a cloud chamber uses supersaturated alcohol vapor to let us see the trails from single atomic scale particles. Each of those little wisps that you see there is actually the track made from an alpha particle, which is really just a fancy word for a helium nucleus. This pin here is smeared with thorium, which is radioactive, and it's an alpha particle source, so it's decaying and emitting individual alpha particles. So each of those wisps that you see is actually a single atom that you're seeing in real time, which I think is pretty amazing. Now, it turns out that all of the helium we have on Earth actually comes from radioactive decay of radioactive elements like radon and thorium. And in fact, as you'll hear about later in the show, radioactive elements are also really important for medical imaging. So, Mr. Wykes, I hope I've convinced you that all of the noble gases are far too important to dethrone. And now, If you'll excuse me, I'm due to have tea with the Earl of the Alkalis. Thank you.
All right, fine, Professor Sprott. We'll keep the rest of the noble elements then, noble gases. But, you know, what about carbon? If we give carbon the boot, global warming will be gone.
Peter, you're not thinking this through. If it weren't for carbon, none of us would be here.
You got that right. Carbon is so important, in fact, that he couldn't be here today. Something about being critical to all life on Earth or something like that. I don't know. But he said that I could make his case for him. That's because hydrogen and carbon hang out a lot. They even have a couple's name, hydrocarbon. Now, they're no Brangelina, but when hydrogen and carbon get together, things can get really fired up. Let me explain. Organic molecules, or molecules that are made up of carbon and hydrogen and some other stuff, are the building blocks for all life here on Earth. So you're made of carbon and hydrogen, your dog is made of carbon and hydrogen, trees are made of carbon and hydrogen, and say things that come from trees, like the paper I have here, are also made of carbon and hydrogen. When things that are made of carbon and hydrogen are given a spark of energy, they catch fire. Like that. Yeah, there we go.
Oh,
Yeah.
hello everyone.
Oh.
So sorry I'm late. It's the carbon dating lifestyle. It's really demanding, let me tell you.
Oh, look who showed up. It's Dr. Carbide. Oh, there we go.
Well, hello there, Dr. H. Well, oh, you have a fire.
Making fire.
That's cool.
Yeah.
It's a really nice fire she has going on here. But I think I can turn it up a notch. Would you like to see me?
Do it.
Would everyone like to see me try?
There you go.
All right. Well, don't worry. I'm going to share the tricks of my trade. So, because fire takes air to survive, if I rotate the air, I can rotate the fire. That's called a fire tornado. But how can I rotate the air? Oh, whoa. This thing, yeah, a screen, right? So, if I use this screen, I can spin it. And as the air moves in from the sides, it's forced to spin too. When the fire consumes the spinning air, it'll rotate. Shall we try it? Yeah. All right, let's try it. Yeah. All right. Okay, well, air is not the only gas we have to deal with. Other gases can show different properties than air. For example, carbon dioxide might be a gas you've heard of. That's when I choose to hang out with two of my oxygen buddies. Now, don't get me wrong, carbon dioxide is in no way a replacement for the air, but it has some interesting properties, so let's check it out. Oh, whoa, I have some candles here. Do we have any birthdays today, this month? Yeah, all right. Okay, how about this year? Do we have any birthdays this year? All right, let's celebrate all the birthdays this year. So I'm gonna light the candles, and you should all think of birthday wishes, and we'll blow the candles out, but not in the traditional sense. Oh, no. I'm Dr. Carbide. I gotta spice things up. All right, we got them all lit. Does everyone have their birthday wishes ready? Great. Now remember, don't say them out loud, because you know what happens if you say them out loud. All right, let's have some birthday music. All right. Everyone has their wishes ready? Let's try to get them all in one. That's how physicists blow out our candles. Now, that reminds me. So, for those of you who did make the birthday wishes, we got them out on the first try, which means your birthday wishes are more likely than not gonna come true. So good job, everyone. Okay, but what happened? Why did the flames go out? Well, it turns out that what I had in this container was carbon dioxide. Carbon dioxide is heavier than air. So when I tilted the container over, the carbon dioxide flowed out. It got to the bottom of the trough, it flowed down the trough, pushing the air out of the way. All right, well, Mr. Whites, I hope you can finally see that carbon, oxygen, and hydrogen definitely deserve our place on the periodic table, and in no means, way, shape, or form shall we be taken off of it. All right, Dr. H, I'm pretty sure we've made our case here. But there's some folks in northern Wisconsin that are freezing right now. They need our help to keep warm. Should we go help them out?
Let's do it.
Let's go help them out. Bye,
All right.
everyone.
All right, let me use my slide rule here and do a quick calculation. Divide by pi and... Aha! This might just be a wild gas, but I think we can take nitrogen off the list. You know, we already have 2 other elements that end in gen, and surely we don't need a third.
My name's not Shirley, but Peter, I'm aghast at that thought. In fact, without nitrogen, it would be the end of the world. And to demonstrate, I've enlisted Professor Air N. Barr, who's well known for his own gaseous emissions.
Oh, Professor Sprott made it look so easy. Some other clown got carried away. All I did was ask him to just get the oxygen out of my tires. Well, the good news, they're only flat on the bottom.
Well, you know, you could use some of the gases that they've been talking about, like hydrogen, helium, or even oxygen.
Pete, think about it. Hydrogen, as we saw, can be explosive. Helium is super rare. And don't get me started with oxygen. You know, the atmosphere is about 80% nitrogen, and that's a good thing. Nitrogen just doesn't react the same way as oxygen does, and that's really important. My friends, we have here a device we call the ping pong ball bazooka. Ooh. Our task? This brass block, we want to tip it over. But if you weren't listening, all we have is this eensy-weensy ping pong ball. You may laugh, but the end is nigh. Because we have already sealed off with tape both ends of the tube so that when I turn on this vacuum pump here, it pulls all of the air out of the tube, leaving a vacuum. That means that there's still 1 atmosphere of pressure, or my namesake, 1 bar of pressure on the outside, and almost none on the inside. I think we're already there, so I'll close this valve and turn this off. This could be a little bit loud, so you may want to cover your ears, and I could use a little help with a countdown starting at 3, 2, 1. Oh! Apparently, Professor Sprott missed the weather report for snow, just not ping pong ball flakes. Oh, that was fun. You know, nitrogen can be put to use in other ways. By the way, did anyone hear about my pets? Not my dogs, or even Schrodinger's cat. Nice kitty. I hope it's still alive, but it could be dead. Oh, but not those kind of pets. PET, in medical physics, positron emission tomography. A radioactive isotope of nitrogen, N13, is used in medical PET scanners. And the way it works is it decays by emitting a subatomic particle called a positron. Of that, I'm positive. And it has a half-life of about 10 minutes or so. Unfortunately, to make it, we need a cyclotron. And sadly, the closest one is across the street. But I can show you what half-life means using another radioactive isotope, barium-137, which has a half-life of about 3 minutes. Drip, 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 drip. I think I've gotten it all out. And now transfer it to the stage and push it in front of the detector. And you can see that it's going up, 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 about between 4,000 and 5,000 counts a second to begin with. Now, watch what happens with time. Every 4 seconds, a new data point will appear on the screen. Now look, 4 more seconds, there. Then another one, 4 more seconds. Now, is the number of decays increasing with time or decreasing with time? I think I heard decreasing. The curve is going down. That's decreasing number, but good guess. Nitrogen in the room does other things. It's a gas, it's a molecular gas, and it's moving all the time, back and forth and back and forth. And it collides with each other. It also collides with very small particles in the atmosphere, be they dust or pollen or smoke. That back and forth motion was discovered by a botanist by the name of Robert Brown, and it's called Brownian motion. It's this very fine motion back and forth. Now, if Steve has prepared some smoke, we can see it in this special microscope stage and the camera. Let's test, see. Oh, plenty of smoke. I thought you were going to quit. It's incense. Oh, okay, that's okay. So you can see the smoke here. I will close off the glass beaker and blow into the tube, transferring the smoke into the microscope chamber. I have to turn on a laser light so you can see the smoke particles because they will scatter the laser light and look green in the microscope's field of view. So now I have to blow in and transfer the smoke. Let's see. You see that? That speckling, the back and forth, that's the Brownian motion to move particles around in the atmosphere. You know, nitrogen also has a very, very useful boiling temperature, a cool minus 196 Celsius. But if you don't like that scale, you can also say it boils at minus 320 degrees Fahrenheit. And at that temperature, liquid nitrogen is very important for keeping things in cold or cryogenic long-term storage. But it's boiling. And when nitrogen boils, or almost anything boils, it goes from its liquid phase to its gas phase and expands 750 times, give or take, when it does so. And I think I can take advantage of that behavior. Imagine me, a lowly jester. Actually, now I'm a knight in shining armor. It could happen, you know. And I have a cannon, just like this one here. But I don't need gunpowder. I have boiling liquid nitrogen right here. And I want to show you. It's boiling. Now we will pour it into the barrel. Ooh, this is going to be fun. All right, get my aggressions out. Here's my projectile, a rubber stopper. Let's put her in.
Fire when ready, Gridley.
No problem. Nitrogen in the hold. Oh, hey! Well, Mr. Wykes, surely you can see to it that nitrogen stays in the periodic table. As for me, I've got to go. I'm out of gas.
Well, Professor Sprott, maybe nitrogen should stay, but surely there must be something we can cut. You know, I hear that silicon is nearly worthless.
Not at all, Mr. Wykes. In fact, silicon is the basis for all of our modern electronics gadgets. And if you don't believe that, our next visitor will hopefully convince you. Please welcome Dr. Sandy Glass.
Indeed, Professor Sprott, silicon is very important for its electrical properties due to its nature as a semiconductor, as my outfit attests. Unfortunately, I will never get to be a full conductor. I can't keep the beat. Now, unlike the other elements we've talked about today, we encounter silicon as a solid, not as a liquid or a gas. It makes up over a quarter of the Earth's crust, usually in the form of silicate minerals. And these minerals can get ground down to sand, and sand can be very useful in a physics demonstration. So here I've got a plate sitting on top of a speaker with sand on top of it. And I'm going to turn on possibly some annoying sounds, and we'll see patterns emerge in the sand. Now the sand landed where the plate doesn't vibrate in locations we call nodes. Silicon is also quite light, and we're going to use that property in our next demonstration. It's one of the ingredients in dry erase marker ink. And I'm just going to draw on this plate a couple of fish. And some bubbles. And I'm not a musician or an artist. Now, can I get a volunteer who's going to be tall enough to stand here and reach over to come down? Let's see. In red right there, can you come on down? So in this ink, we have silicon, some other chemicals, and some alcohol. And we're waiting for that alcohol to evaporate for our ink to dry. And as my volunteer makes her way down, now you can stand right up in front, and you'll get to watch what happens live while everybody else has to watch on the screen, and then I'll have you do something at the very end. We're just going to pour some warm water onto our plate.
Is that just regular water?
Yep, just regular water. And as we watch, the bubbles are moving, and soon our fish will be floating too. That silicon ink is lighter than the water, less dense, and can float on top. They're swimming around. Now, what's your name? Hi, Ruby. If you'd like, you can reach your hand over and put kind of the backside down, and you can actually transfer one of the fish, kind of like a temporary tattoo, to the back of your hand if you'd like. That's good. Just very quick touching it. Good job. Excellent. Thank you so much. Now people quickly realized they could melt down that sand and make glass. And glass has been very useful throughout human history. We can make magnifying glasses with it. And that same lens, when held further away, is like the converging lens of a telescope. And now I look upside down. There's other useful things we can do with glass too. We can stretch it into very long fibers that we call fiber optics. And they allow us to send laser light signals over long distances. In fact, this allows internet signals to cross the ocean. So here's a simple laser pointer. Here's a fiber optic cable. And you can see the light exiting at the end. Now this works because the glass internally reflects that light, only letting it out the end, not the sides, as you can see better with this setup. Now glass is very useful because it transmits most wavelengths, which is why it makes a good window for us to see out of. Now this is an infrared camera, and it looks at the wavelengths that correspond to the temperatures of our own bodies. So let's see what our audience looks like in the infrared. Fantastic. You guys are picture perfect. Now, if I put this pane of glass in front of my camera, though, I won't be able to see you anymore. Instead, the glass acts as a mirror in the infrared, and we see me.
But Dr. Glass, we already have modern-day plastics that do the same thing.
That might be true, but we haven't talked about the electrical properties of silicon yet. I have here an array of solar panels, and they're attached to a motor. Now, sitting here just in these fluorescent lights, they're not doing anything. They're not able to take these lights and turn it into electricity. But if I turn on this bright lamp that can mimic the sun, now our motor turns. We've turned this light into electricity, and that is mighty useful. Now, silicon may be abrasive. It is in sandpaper and some toothpastes, but it's got a softer side too. It's in silicone caulk and lubricants. It even puts the silly in silly putty. Without silicon, we wouldn't have computers, cell phones, or video games. And that would be a bummer.
Well, Professor Sprout, I think we can get rid of some of the common metals like copper, zinc, nickel. I'll pick one, copper. Many of its properties are not that useful and are also duplicated by other elements.
Not at all, Mr. Wykes. In fact, copper is very important, not only in physics, but also in the arts. If you mix copper with tin, you get bronze, like this bronze statue of a badger outside the governor's office. Or if you mix copper with zinc, you get brass, like this statue of the Fonz from the Happy Days TV show. So we have with us today that famous metallurgist, Professor T.L. Copper, who works on the minds of young students. Or maybe he just works in the mines.
Thank you, Professor Sprott. I think maybe you should just mind your own business. So yes, I am T.L. Copper. TLC are my initials, Tender Loving Copper, and I'm here to talk about the wonderful and unique properties of that namesake metal of mine, copper. Did you know, first of all, did you know that the atoms of copper have mass? But only the Catholic ones. Okay, all right, I was going to tell you some more jokes and puns about copper, but I can see you don't appreciate them. So let's start by talking about some of the properties of copper. One of the properties of copper is it's one of the better conductors of electricity. And that means each copper atom can take its electron and move it readily from atom to atom. We call that electricity or electrical current. And copper is one of the better materials that does that. Now, one of the principles of physics is called Faraday's law. And it says that if you take a magnet and move it by a good conductor, and I have a bar magnet here, it's similar to what you were looking at earlier, and you move it by a good conductor, and here I have a coil of copper wire, you will create an electrical current. So I take this bar magnet and I simply put it in the coil of wire, and we can see the current here on this galvanometer. It's just a device that measures current and shows you current. If I pull it out, I get a current in the opposite direction. So I can go in and out, and I get a current. In fact, I get an alternating current here. What I've created is a human generator or a human alternator is what I've done by doing this. And you notice that if I keep the magnet in the coil, I get nothing. It has to be moved past the conductor for it to create a current. Now I can also show that with this device here. This is a larger magnet. It's a hockey puck. It's neodymium, okay? And if I take this stronger magnet, and this is a coil of copper wire that's just plastic coated, if I take this stronger magnet and pass it by this coil, I will create a current also. But this time, it's not connected to a galvanometer. Instead, it's connected to an old-time flash bulb from an old-time camera. So in just a moment, I'm going to do this. This is going to be fairly bright. So I'm going to put a shield over the top of it, and I urge you to look kind of off to the side here a little bit versus right at it. So I need a countdown. 3, 2, 1. As you can see, I created enough current for the current to go inside the bulb, excite the gases inside, and blow up the flash. Now another property of copper is it's a very good heat conductor. It can move heat from one point to another very readily, and I can show that with this gadget over here. Here I have a burner, and I'll start it up. And this burner's right underneath a rod. On this side, I have a copper rod. On this side, I have a steel or iron rod. And the burner is just simply going to create heat into the center. That heat is going to be transferred out the rod. Each rod has 6 marbles on it, and they're held in place. The marbles are held in place with beeswax, which has a tendency to melt when it gets hot. Now, this will take 2 or 3 minutes to happen, so keep an eye on this as I go forward, and then we'll come back to it in a couple, 3 minutes. All right, I now need a young volunteer to help me in a copper race. You right there, come on down here. All right, can you stand over here? And your name is? Nevaeh. Nevaeh? Okay, Nevaeh, thank you for coming down. Nevaeh, would you take that ball? Do you like my hat, Nevaeh? Yeah. Yeah. Just remember, you too can be a physics professor someday and wear a hat like this. I can tell that impressed you. Okay, here's what we're going to do. Will you look down that copper tube, please? Anything in there? Okay, will you look down this copper tube? Is there anything in there? Okay, they're both hollow. Okay, Nevaeh, will you stand over there again? Here's what we're going to do. You're going to take your ball, and I'm going to take this steel ball, and at the count of 1, 2, 3, go, we're going to drop our ball down through the tube, and we're going to have a race. And you're going to try to catch it. You put your hand down here like this, and I'll put my hand down here, and we'll see who wins the race, okay? Simple? Okay, on go. 1, 2, 3, go. Whoa, Nevaeh, wait, give me 5. All right. She really beat me, didn't she? Okay, let me have the ball back. Here, let me give you my namesake. Here's a copper for you for helping me out. Let's give her a hand here, okay? Thank you, you can go back. As you can see, I've lost some of my marbles already, okay? All right, so how was Nevaeh able to beat me so badly? Is there gravity different over here versus here? No. Both tubes are identical. Here's what happened. Her ball was simply a steel ball. My ball, on the other hand, was a magnetic ball. And as that magnetic ball fell through the copper, according to Faraday's law, it created a current in the copper. There's a second law of physics called Lenz's law that says that once you create a current in the copper, it creates an opposite magnet to the first one. So as the ball went through, it was like 2 magnets opposing one another, and it went through very, very slowly. Okay, I'm going to stop over here before I lose all of my marbles. And as you can see, I have lost 4 marbles here versus only 2 here. Copper was a much better conductor of heat. That's the main reason that your more expensive cookware and fry pans a lot of times are covered with copper on the bottom, because the copper distributes the heat very readily, very evenly throughout the pan, versus a cast iron pan, hot spots, slower heating up. Now I can also show you Lenz's law that we just talked about with my neodymium magnet again. This time I'm going to take the magnet, and I just have a huge plate of copper right here. And I'm going to take that copper and I'm going to drop it, or I'm going to take this magnet, I'm going to drop it on the copper plate from a few inches above. Watch what happens. It slowly goes down. I can put it on its side, tip it over, and it slowly tips over. Since the beginning of the show, I've had this plate of copper sitting in liquid nitrogen. As they talked about earlier, minus 320 degrees Fahrenheit. So this plate of copper is a much better conductor than the room temperature one. In fact, it's about 5 to 10 times better a conductor. So if that's the case, I get a better opposite magnet, and I can drop this from a higher level. I can pull it over on the side here and push it over, and it slowly goes over. And if I do this just right, I can take it and put a spin on it, and it goes down. At the end of the show, if some of the kids want to come up, we can show you this again, and they can drop it on there. All right, for my final demonstration then, I'm going to use this apparatus here. And this is just a large capacitor. And all a capacitor is that you take and you can put a lot of electrons in it, a lot of energy in it, a lot of electrons, and then release those electrons and create a large current. And that large current is going to go through this copper coil right up here. And in that copper coil, I just have a soda can, an aluminum soda can. Aluminum, my sister metal, is a very good electrical conductor. Not as good as copper, but still a very good electrical conductor. So I'm going to put this in there, like so. Hey, Evan! Good catch, Evan. So you see, Mr. Wykes, copper has many, many unique and wonderful properties. We can't get rid of it. In fact, copper makes perfect sense.
What's that horrible music? Who are you?
I'm Iron Man.
Well, you're not quite what we expected.
What do you mean?
Well, we thought you'd be someone more like Tony Stark from the Iron Man comics.
Oh, don't get me started on Tony Stark. I used to work for Tony Stark.
Oh, really? What did you do?
I used to iron his suits. Worst job ever.
Ah, so you would be in favor of taking iron off the periodic table.
Oh, whoa, whoa, whoa. That'd be a really bad idea for a lot of reasons. None of you would be here if it wasn't for iron. We'll get to that. Let's start off with something a little easier. Hey, that's a nice barn. Who can tell me why did they paint barns red? The reason they paint barns red is because red paint is cheap. Yeah, the red pigment in red paint is called red ochre. It's rust, iron oxide. And iron oxide is cheap and plentiful. Iron, or as the chemists like to call it, Fe. Iron is the most abundant element on Earth by weight. Now there's a catch to that. Only about 6% of Earth's crust is iron. Now, that's still a lot of iron. That's where we can get at it. Most of Earth's iron is in the middle, Earth's core. Earth's core is over 80% iron. So where did all that iron come from? Exploding stars. We're going to pretend that this ball is our sun. And let's pretend that that thing is a much bigger star. It's like 8 to 50 times the size. It's a big star. And it's about to get even bigger. Hey, you remember from earlier in the show what makes stars work? Shout it out. Hydrogen, right? Hydrogen, where you take those two little hydrogen atoms and you squeeze
Woo!
them.
Hydrogen! Yeah, let's go! Woo!
Yeah. You take the hydrogen, you squeeze it together in a process called fusion, and bang, it turns into helium.
Yeah, helium, on guard.
Get out of here. Okay. Hydrogen, fusion, bang, helium, and it releases a lot of energy. So it's really hot in there. All those little atoms inside are zipping around really fast. So why don't they just zip off into outer space? It's because of something called gravity. Gravity is where stuff pulls on other stuff. So it keeps everything in balance until you run out of hydrogen. Then the star starts collapsing, but when it does that, it starts heating up. And when it reaches a point, it'll heat up to the point where it starts fusing the helium atoms together to make things even heavier on the periodic table, like lithium, carbon, and so on. Now it gets even hotter in there, and now the fusion energy starts winning, and the star starts expanding. So we keep on making heavier and heavier elements in the periodic table. The star gets hotter and hotter. When's it all going to end? When we get to iron. See, if you fuse lighter elements, they give off energy. But if you fuse iron or heavier elements, it takes energy. That's bad news for our big star. No more fusion energy, no more balance. Gravity wins, and this thing comes crashing down really fast. I mean like 150 million miles an hour fast. So in a few seconds, that star collapses down, crunches down the core. Wham! The temperature and pressure inside that core gets really high, like 100 billion degrees. At those temperatures, iron and some elements could start fusing and making even heavier elements. Many of the elements you see on the periodic table are formed that way. But there's more. When that crunches down, it bounces. And there's a huge explosion called a supernova. In a few seconds, that explosion releases more energy than our sun will give off in its entire lifetime. So that all those heavier elements, including a lot of iron, gets thrown out into outer space. Now, some of that iron makes its way here to Earth, and that's why barns are painted red. Hey, you know what else is red? Your blood. And it's also because of iron. There's a very important molecule in your red blood cells called hemoglobin. And it has a very important job. Its job is to take oxygen from your lungs and spread it out to the rest of your body. So wait, how does that iron get into your body? You eat it, of course. I know, nail biting is a really bad habit. Don't eat nails. That's not how you get iron in your body. You get iron from the foods you eat, and particularly foods like clams and oysters and liver and spinach and tofu. You know what? This nail's starting to look pretty good. Or, don't eat it? Okay. Or you could eat foods that have had iron added to them, like fortified cereals. Yeah, they actually add iron to food like breakfast cereals. And I'll show it to you. Now, in a few minutes, I'm going to tell you how to do a version of this experiment at home with adult help. Hey, wait, I need a helper right now. Who wants to help me out? Somebody who's not already been down here. Who wants to help me out? Okay, Wisconsin shirt, way in the back. Come on down. Quinn, step right over here. So Quinn, a little before the show, I put some of this fortified cereal into this along with some water. I think we need to stir it up a little bit. Let me set this down. Can you push that big button down for me? All right, we're going to stir it up really good. You think that's good? I think that's good. Okay. So now I also have something special here. This is a magnet. What color is that plastic? White. So we've got some white plastic on the outside. This is a very special magnet. It's called a magnetic stirring rod. Quinn, will you put that in the bottom of this jar for me, please? Great. Now, shall we see how this looks? Let's see here. Yum, 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 yum. Oh, take a smell. It's disgusting. It's really disgusting. Hey, Quinn, let's pour that in here. Pour it all in there, nice, quick. There we go. Get all that good glop in there. Yeah. Okay, go ahead and set that down on that. Now, Quinn, I got one more job for you here. Would you flip that switch on? I told you this is a magnetic stirring rod. See, inside of this box, there's a magnet attached to an electric motor. As that magnet gets spun around by the motor, it makes the magnet inside the jar spin too, and it stirs it up. You think it's stirred enough? No? Gonna let go a little longer? Okay. How about now? No? Longer? How about now? Okay, sure. I'll go ahead and turn it off. You can't be too careful about these things. Okay, let's see if we can't fish that out. Ah, there we go. You notice anything different about our white magnet here?
Turning black.
Yeah, you know what? I'm going to take this over here to the camera. You stay right here, Quinn. I'm going to take it over here so everyone else can see it too. You notice the difference?
Why is it turning black?
It's turning black because that's iron that came out of the cereal. Yeah. Iron is attracted to magnets. So the iron that was put in the cereal got attracted to there, and we can see it. It's right there. Quinn, you did a great job. Let's give her a big round of applause. Thank you very, very much.
Now I can see how ironic it would be to remove iron and related elements from the periodic table.
Mr. Wykes, you might want to lay off the iron jokes. That last one was a little rusty.
Whatever. Hey, I've got a good question for you. How can we tell that all of these elements that you talked about are in exploding stars? You know, exploding stars are really far out in space.
That's a really good question. And it turns out that all elements have a unique fingerprint. It's called its light spectra. So if you put energy into an element, it gives off very specific colors. So if a scientist aims a telescope at a star, even if it's on the other side of the universe, they can tell what's in that star by what very specific colors are coming from that star. And we're going to try this out. So listen carefully. I'm going to have you put these on. Now you can either watch on either side here on the screen, or you can put the glasses on as soon as we turn the room lights off. All right, there's hydrogen. Ooh, you'll see color bands on either side. See them? Like I see a red one and a blue one and maybe a purple one. Nice. Oh, yeah. All right, let's try another one. Let's do helium.
Yeah, helium.
Ooh, see how much different that is? We got a whole different set of colors. All right, now let's try nitrogen. Whoa, wow. Look at all that. All right, now let's do carbon as carbon dioxide gas. Wow. That's beautiful. Now let's turn the room lights back up. We're going to do some more elements. We're going to just do them a little different way. If you take some elements and put them into a hot flame, you'll see the colors in the flame. So we're going to start off with silicon.
Excellent. I found this thumb drive backstage, and it's got a large silicon chip on it, so I figured we'd use that.
Whoa, that's my thumb drive. I'm sorry. That has my students' grades from last semester. Nah, that's not a good idea. Thank you.
I was afraid of something like that, so I also grabbed this cell phone.
Oh, yeah.
Whoa. No. This has got all my game apps in it, so no.
How about we just skip silicon? How about some nice iron? Let's bring the room lights down. Everybody keep an eye on the flame here. And here's what iron looks like. I like the sparkles. Okay, now let's look at copper. This is my favorite. This is really cool.
Copper's the best.
And that's how you can tell what's in a star, even on the other side of the universe.
So you see, Mr. Wykes, we can't change the periodic table. All of the elements are what nature has given us, and they're all important and useful. In fact, maybe we should have a new government agency. We could call it the Element Protection Agency, the EPA.
Well, Professor Sprott, I am impressed by all of your colleagues and showing me just how important every element is on the periodic table. And if my great-grandfather Mendeleev were still here, he would be very happy to see everybody standing up for his periodic table.
Well, I hope you're successful convincing our funding agency to abandon this crazy idea.
Yes, I am going to contact them immediately.
Okay, well, I wish you every success. Now, of course, our funding agency hasn't really made such a ridiculous demand. But you know, our politicians do sometimes misunderstand the role of science and how important it is. We laugh that 120 years ago, the legislature of Indiana considered a bill to redefine pi to be 3.2, but they were wise enough not to vote on it. Science is about facts and not about opinions. We hear a lot about alternate facts, and mentions of climate change are being removed from government websites. Let's hope that our present legislature will be at least as enlightened as the one in Indiana 100 years ago. Now, not everyone should be a scientist, but everyone should understand what science is, why it's important, and why it should be funded. And I hope you'll join in the effort to make that happen. Now, I'd like to end the show the way we've ended every one of the shows over the past 36 years, by making for you a cloud, using a liquid form of the element nitrogen. Here I have a container with 25 liters of liquid nitrogen. We force nitrogen gas into the container. That forces the liquid up into this copper pipe on the top, which has several dozen small holes. When the liquid and the gas comes out, it is still very cold, and it comes in contact with the warm air, and the water vapor in the air condenses into tiny droplets of liquid water. And that's what we call a cloud. And with that, I thank you all for coming.